Hi, I'm Ben-Yaakov. This presentation is entitled Deciphering the Current Feedback Amplifier, or CFA, and including bandwidth and stability. There are some relevant references to this presentation. There is a paper, this is the paper, and there is a video. And I'm going to print the links to these references in the description section of the video that you are now watching. So let me say a few words about the background. Now there are actually three types of operational amplifier: the voltage feedback amplifier, VFA, the transconductance amplifier, TCA, and the current feedback amplifier that we are going to talk about, and this is the CFA. Although they look from the outside sort of similar, these amplifiers are fundamentally different in terms of the inner structure, behavior, and closed-loop transfer function. In the VFA, the closed-loop gain times the bandwidth, this is the gain-bandwidth product, is constant. On the other hand, in the CFA, the bandwidth can be maintained constant over a wide range of gains, a behavior that actually looks a bit mysterious. So in this presentation, I'm going to explain what is the CFA, the reasons for its gain-bandwidth behavior, and some issues of stability. So here are the differences which are important, and that is the gain bandwidth of the VFA is constant. That is, if you need a higher and higher gain, then the bandwidth is going to be smaller because this is the limit of the open loop gain. On the other hand, in the CFA, you can maintain the bandwidth about constant while you can change the gain. So it is really fundamentally. So let's see what is the difference between the VFA and the CFA, the voltage feedback amplifier and the current feedback amplifier. The basic structure of the VFA is a differential amplifier at the front, then we have the main amplifier, and then we have an output stage for delivering the current to the load. Very important to realize that the voltage between the two inputs, that is the difference here, vis-a-vis I call it, is the error signal. And this is where we compare the reference to the output. So the difference is developed here and then amplified. So this is the sense signal of this structure. On the other hand, the CFA looks quite a bit different. First of all, there is no symmetry between the two inputs. We have here a follower, a unity gain amplifier. Actually, it's sort of a emitter follower. And then we have this resistance, which is the internal resistance of this amplifier. It's not a resistance that we usually add. And the error signal is the current in this resistance. So this is where we compare again the reference to the feedback. The difference develops here, and then it is controlling a dependent current source which feeds an RC circuit. This is not really an RC network that is put in, but it is usually the parasitics of the circuit itself, that is the resistances and the parasitic capacitances. And then the voltage developed here is then fed to the output amplifier to deliver the current to the load. This is just a buffer for getting a high output current. And here is a simplified description of a CFA. This is by Analog Devices, this particular unit. We have here the unity gain amplifier. This is between, say, this transistor. This is a PNP transistor, an NPN transistor. We enter here, this is the output, and then the output actually is here. The reason for having two transistors is to subtract the base to emitter voltage, the DC voltage. So we start with a DC level here and end up with about the same DC level here. The gain, however, is 1 because actually a two cascaded emitter follower. Now, since we like to have positive and negative current, we need to have two sections here. This is, let's say, for the positive current, and this is for the negative current, so that it is a bidirectional amplifier, not just one direction. And then we have the intermediate stage, which you can see is sensing the current here. This is a current mirror, which is sensing the current of this transistor and this transistor, which is the output current. So we are sensing the current here. We don't see RE. RE is the resistance of this emitter, as a matter of fact. And this sensed current now is transferred with the gain to this stage here. Now the RC is the parasitic resistance and capacitance in this region. And then we have a buffer amplifier, push-pull, for the output. So this is the structure, which is entirely different from the VFA. To analyze the behavior of the VFA, we have to use a generalized feedback system. I've described this approach in a paper which is here given as a unified approach to teaching feedback in electronic circuits. It's a paper that was published many years ago. And the difference between this approach and the conventional one is the addition of this G, which turns out to be very important. The link to this paper is given in the description section of the YouTube video that you are now watching. So if we have a G block here, it's a gain block or transfer function block, then we're going to have the regular feedback transfer function, which is this A over 1 plus beta A times G, because G is sort of multiplying everything. Now when beta A is much larger than 1, and this is in the useful range of operation, we see that the gain becomes G over beta. It is important to emphasize that there are many circuits with feedback that you cannot analyze in a simple way if you are not introducing the G. And I'm demonstrating it here with this inverting amplifier, okay? So G is the transfer function, let's have a look at it, between the input and the summing junction, okay? While beta is the transfer function between V out and the summing junction. So here the G would be between V in and the voltage here, and beta will be the transfer function between the voltage and the input voltage here, the input signal here. And then beta is Rin over the sum of the two resistors. G is this RF over Rin plus RF. When we divide the two, we get the familiar transfer function of an inverting amplifier, RF over Rin. So it's very simple, but again, you do have to introduce this G. Very, very important. Now, it is important also to realize that in the VFA, G and beta are linked. You cannot change one without changing the other. For example, if you change Rin, you change beta, and then you change G2. Or RF. If you change RF, it will change both G and beta. So this is a limitation, you might say, of the VFA, and as we will see, the major benefit of the current feedback amplifier, the CFA, is that you can change each one independently. We'll see it in a couple of slides. So now I'm going into the CFA. Again, the structure is that we have a follower here, we have the RE, the signal is the current through RE, the sense signal, which is then fed actually to the Z with some amplification, of course, and we have the V out. And now I'm looking again at an inverting amplifier. These are the input terminals here. This is the output, here is the RF, and here is the Rin. Okay. Now, in order to get the transfer function, we have to find G and beta. Okay. Now again, G will be the transfer function between V in and RE here, and beta will be between the output voltage and RE here. Okay. Now we can derive this transfer function, and I'm not going to do it in a formal way because it just takes a lot of derivation. Let me just say that the result is that in this particular case we get again RF over Rin, so that RE, R sub E, is not affecting the transfer function in closed loop. Okay, so that from outside this amplifier looks like a regular VFA, a voltage feedback amplifier. Now, although I'm not deriving the transfer function, here are the two networks for deriving it. Okay, this is for G between V in and the current here. So G is one of this current over V in, and for V out is between the voltage and the current here. Okay, so I'm not going to derive it for the reason that I've said, but I'm going to show it in a different way, in a more intuitive way. And here it is. Let's assume that indeed the output is RF over Rin. Okay, let's assume that this is the case, and which means that this is actually G over beta. Okay, so let's find the voltage here, and I'm at this point removing RE. This is RE here. Okay, this RE. I'm removing it because I'm talking about the transfer function between here and here, here and here, with the voltage here. Okay, I'm talking about the voltage, and I'm removing RE. And I'm assuming that V out is minus RF over Rin, sort of guessing the result. Okay, so as I look at the voltage here, we have a transfer function this way and then this way. So the voltage here is the sum of this expression plus this expression. Now that we have the result, we are guessing the result, RF over Rin minus, then I'm replacing V out with this value, and lo and behold, as you can see, these two terms cancel out. What does it mean? It means that the voltage here is 0, so that it will be independent on the resistance that I'll put in a real circuit. Okay, and this is because the voltage here is very small. Obviously it's not 0, but it is the error signal depending on the open loop gain, but it is very, very small signal. And this is just showing that the fact that we do have this RE is not affecting the transfer function from outside. It looks like a regular VFA with the transfer function that we are familiar with, but there are some differences in the bandwidth that I'm going to talk about. Okay, so the transfer function per se is not different, but there is a difference in the bandwidth, and this is what I'm going to talk about in the next slides. Now, another way to look at it, also in an intuitive way, is to say that RE is small. Indeed, RE is usually a small resistance. This is the output resistance of a emitter follower. It is small. So if it is small, and now this RE is in parallel with RF, which is larger than that, and Rin is also larger than RE, then G, which is the current here over the voltage, becomes 1 over Rin. Very simple, okay? Because that's what we are left with. This is the current going here. Same thing goes here. Beta is 1 over RF, and again, since the gain is G over beta, we get again this RF over Rin. There is a matter of a sign here, which is dependent as to whether you enter the positive or the negative terminal, because this will affect the output. That is, the question is whether Z can be considered in a certain connection as positive or following the sign or inverting the sign, and this is causing this change in sign, so that in fact the actual gain is minus RF over Rin. And I'm showing it here that if the Z itself has a phase reversal, then the transfer function between input and output will be negative. If, however, the reversal is in the feedback and this has no phase reversal, then the gain will be positive. Okay, so but this is a fine point that is really not a major point in the discussion that we have here. What is important to realize, I'm going back here to this slide, is that as we can see here, G is a function of Rin and beta is a function of RF. So G and beta are independent. You can change one while the other one can be kept constant. This is in contrast to the VFA, as we have seen, that you cannot change them independently. So this is the major point of the current feedback amplifier, that you can change G and beta independently. Now beta is affecting the bandwidth. This is a regular feedback system, and we know that in this feedback system, doesn't matter how it is realized, the gain bandwidth is constant. Here it is. Now, however, we have another degree of freedom, you might say, with a G, which is sort of can change the total gain. So the bandwidth is affected by beta here, while you can then trim the gain by G. And this is the whole point. The point is that in the current feedback amplifier, you can change G and beta independently. You can fix beta and then trim the G for the gain. So the conclusion is that if I keep this resistor, which is determining beta in this case, inverting connection, and this is the non-inverting connection, and this R1 and RF are actually determining the feedback at beta, and if I keep it constant and change R2 or Rin here, which are determining the gain, I can change the gain without affecting the bandwidth. This is the whole point. To demonstrate this, I've set up a simple LTspice simulation around this amplifier, LT1229 of analog devices. I have here some sense and excitation voltages. I'm not going into it. This is just this connection that we talked about. In this case, it is like a inverting. And here it is. First of all, the inner transfer functions. In particular, we have here the Z. This is the transfer function between the output and the current across RE. That is this current here. This is the negative part. This is where the output of this unity gain amplifier. And here I have the actual resistance, which is calculated as the voltage across the terminals divided by the current. Okay, so this is RE, and we see that RE is about 100 ohms or so, while Z is characterized by a first order system. You see it's a 90 degree, this is the 90 degree shift lag, and then we have at a high frequency another pole, and this will be beyond actually the operating point. So it is very nicely shaped naturally because it's just a single RC network, and then we have a break point here, and then a drop of 20 dB per decade plus a maximum of 90 degree phase shift, and then we pick up the next pole. And now here is a demonstration of the major difference between the current feedback amplifier and the voltage feedback amplifier. Here I'm keeping G fixed and I'm changing beta, and as you can see, the bandwidth is changing from here to here to here to here. So we can clearly see that beta, being a feedback path, is changing the bandwidth. And now here's the case, which is kind of surprising in fact, that you can fix beta, that is fix the bandwidth, and then change G to change the gain. So we see here that the gain is changing while the bandwidth is about constant. Now the change in the gain is about 100-fold, okay, that's 40 dB, it's 100. If it would have been a VFA, then the bandwidth, say from here to the higher gain, would have changed 100-fold, okay, that's a lot. While here it's a little bit shifted, here you see it's much less shifted, so we see that we can fix the bandwidth and change the gain. And this is of course making the CFA a very good candidate for a high bandwidth amplifier, because there is no penalty when you change the gain. So let's talk now about the bandwidth and stability, which is a little bit different from the VFA. Now I'm using here now the concept of 1 over beta and its relationship to the open loop gain. Now this approach is explained in this video, so if you are not familiar with it, I'm first of all recommending very much that you will, because it's a very powerful way of designing feedback in analog and power electronic systems. And what it is in a nutshell is that you start with the open loop of the system. In this case, this is the Z, the impedance of the system, and then you present here the 1 over beta. The intersection here is when 1 over beta is equal to A, meaning that beta A is equal to 1. So this will be actually the break point of the loop gain. And in fact, this distance is the loop gain. Furthermore, by looking at this, we call it the rate of closure here, you can tell whether the system will be stable or not, or sort of estimate the phase margin, which in this case will be something like 45 degrees. And also this point is when beta A is equal to 1 for this 1 over beta. This is the 1. Now since this is a straight line, there is no phase shift to it, and the phase shift is coming from the open loop gain. And as you can see, in this particular case, phase margin is about 45 degrees. We'll see it in a minute. So let's have a look now at the meaning of beta in our case. So this is the G model, and beta in this case, the V out to this current, and I can simplify it if I assume that the R sub E is smaller than R in, R sub E is smaller than R in, then the ratio will be dependent on the impedance plus RE. This will be neglected, okay? So 1 over beta will be RE plus ZF, and in our case, we are talking about an inverting amplifier, then Z sub F is a resistor. So now, going back to the impedance plot, so this is the open loop, and if I'm limiting myself to a phase margin of 45 degrees, this should be 45 degrees, then I'm finding that the minimum value of R sub F plus RE is 400. That is, if RF plus RE will be lower than that, then the phase margin is going to be worse, and then we might have a problem of oscillation. So this is really setting the limit of how small can RF be. So we see that RF is indeed changing the gain, but on the other hand, it is affecting the phase margin very, very strongly. And if RF is smaller, then we do have a problem. So in the general case, we have to make sure that RF is indeed large enough. But there is a special case, and this is the case of an integrator, in which we are going to have a special problem. So let's look first of all at the integrator, which is realized by a voltage feedback amplifier. This is the regular operation amplifier, okay? So this is the circuit, and if I'm looking at beta, this is the ratio between the voltage here and the voltage here, which is this transfer function. And at high frequency, the maximum beta is 1, okay? Because this is when the capacitor is like a short, and then we have the output connected actually to the minus input terminal. So this means that if I have a VFA with a certain A open loop, the minimum 1 over beta is 0 dB, 1, and this is how actually manufacturers are designing the VFA. They are making sure that even for a gain of 1, which is the worst case in terms of feedback, that is the strongest feedback, the system will be stable, so the phase margin will be, say, 45 or maybe larger than that. So this is for the VFA. Now, in the case of the CFA, we have a similar problem. Remember, we said that we need a high Z sub F here in order to limit the current here and to make 1 over beta large enough. So in this case, beta is the current here divided by V out, and I'm simplifying it by neglecting R in, assuming that it is larger than R sub E. So I have here that beta is IE over V out, which is 1 over RE plus the impedance of the capacitor. So if nothing is being done, then we have 1 over beta is RE, which is meeting the open loop impedance at this point. And of course, in this case, the phase margin will be very small, and therefore we are going, in fact, it's negative here. So in fact, this system will oscillate. So this means that the basic integrator with the CFA is unstable. And again, this is because the impedance of the capacitor becomes very small. So the current here is basically V out over RE, and this is at a very low level here. So we are crossing the Z curve at the point at which the phase margin is just too bad. Now the remedy for this is actually to add a resistor here. Now, as we have seen before, the value of this resistance does not change actually the transfer function in closed loop, RF over Rin in the case of just an inverter, and the same will happen with an integrator. So comparing the VFA to the CFA, we can say that the major benefit of the CFA is that it has a much higher bandwidth, and we are removing the restriction that the gain bandwidth product is constant. However, the VFA is better in terms of the bias current, of course. Here, we cannot talk about offset current because the inputs are not symmetrical. The input offset voltage is also worse in the CFA. So the precision of the VFA amplifier are much higher. And also we've seen that in the case of the integrator, we have some problem with the CFA that we can actually solve it. So this brings me to the end of this presentation. I thank you very much for your attention. I hope you found it of interest, and perhaps it will be useful to you in the future. Thank you very much.